People tell me light is both a wave and a particle, like it's something in between. But when I explain this, I say it's neither a wave nor a particle. It's something completely different. And if you don't understand this difference, you're not learning quantum mechanics. You're memorizing a wrong analogy. Let me explain what light actually is. Because this wave-particle duality story everyone tells, it's wrong. Not a little wrong, fundamentally wrong. And it's taught in every physics class like it's gospel. Light is both a wave and a particle. You've heard that. Everyone's heard that. It sounds profound, mysterious, very quantum mechanical, very deep, but it's nonsense. Light is not a wave. Light is not a particle. Light is not both. Light is not either. Light is something else entirely. Something we don't have a good word for in everyday language. So we use analogies. We say wave and particle because those are things you're familiar with. But the analogies break. They mislead. They make you think you understand when you don't. I'm going to tell you what light really is. Not the textbook story, not the popularized version, the actual physics. And it's going to sound strange because light is strange, nature is strange. And trying to force it into familiar categories is what causes all the confusion. Let me start with history because that's where the confusion began. 1700s, Newton says light is particles, little bullets shooting through space. This explains why light travels in straight lines, why it casts sharp shadows, why you can't see around corners. Makes sense. But then there's a problem. Thomas Young does an experiment. The double slit shines light through two narrow slits, and on the screen behind he doesn't see two bright lines like you'd expect from particles. He sees an interference pattern, multiple bands, bright and dark stripes alternating. That's a wave thing. When two waves overlap, they interfere. Peaks add to peaks, troughs cancel peaks. You get the pattern Young saw. So light must be a wave, right? Not particles, waves. 1800s. Maxwell develops his equations, electromagnetism. And guess what falls out of the math? Waves, electromagnetic waves. Light is an electromagnetic wave. Electric and magnetic fields oscillating together, propagating through space. Beautiful, elegant, problem solved, except it's not solved. 1900s Planck is studying black body radiation. Hot objects glow. The hotter they are, the more they glow, and the color changes. Red hot, white hot. There's a spectrum, an intensity curve. And the classical wave theory predicts this curve completely wrong. It predicts infinite energy at short wavelengths, the ultraviolet catastrophe. Obviously wrong. Planck fixes it by assuming energy comes in chunks, quanta. Light isn't a continuous wave. It's emitted in discrete packets. Each packet has energy proportional to frequency, E chi h, f. Planck's constant times frequency. This works. The math matches experiment. But Planck himself doesn't believe it's real. He thinks it's a mathematical trick. Surely light is still a wave. This quantization is just an artifact of how atoms emit light, not a property of light itself. Then Einstein comes along, photoelectric effect, shine light on metal, electrons come out. But there's something weird. The energy of the ejected electrons doesn't depend on the intensity of the light. It depends on the frequency. Blue light ejects faster electrons than red light. No matter how dim the blue or how bright the red, this doesn't make sense if light is a wave. Wave intensity should matter. More intensity, more energy delivered to the electrons, but it doesn't work that way. Einstein says light is quantized, not just the emission, the light itself. Light consists of particles, photons. Each photon has energy at chimes f. When a photon hits an electron, it gives all its energy to that electron. One photon, one electron. The intensity just determines how many photons hit per second, but each interaction is particle-like. So now we're back to particles. Newton was right, not exactly, because the double slit still exists. Young's interference pattern is real. You can do the experiment today. Shine light through two slits, you get interference. That's a wave phenomenon. Particles don't interfere with themselves. So what is it, wave or particle? Both, neither. This is where the confusion starts, and it's been confusing people for 100 years. Here's what textbooks say. Light exhibits wave-particle duality. Sometimes it behaves like a wave. Sometimes it behaves like a particle. Which one you see depends on how you measure it. This sounds wise. Complementarity. Bohr loved this. The wave and particle pictures are complementary. Both are needed. Neither is complete. You can't see both aspects simultaneously. The measurement determines which aspect manifests. But I don't like this explanation. It's too vague, too philosophical. What does sometimes wave, sometimes particle actually mean? When exactly does it decide? How does it know what kind of measurement you're doing? Let me give you a better way to think about it, a more precise way. Light is neither a wave nor a particle. Light is a quantum object. It behaves according to quantum mechanics. And quantum mechanics doesn't say things are waves or particles. It says things are described by probability amplitudes. Complex numbers that evolve according to specific rules. You calculate these amplitudes. You square them to get probabilities. That's it. That's quantum mechanics. Sometimes when you calculate these amplitudes, the math looks like wave equations, interference, diffraction, superposition. So we say it's behaving like a wave, but it's not a wave. It's a quantum object whose probability amplitudes happen to interfere. Sometimes when you detect light, you detect it in localized chunks, discrete clicks in a detector, one photon, one click. So we say it's behaving like a particle, but it's not a particle, it's a quantum object whose probability amplitude has collapsed to a localized detection event. The wave behavior is about how probabilities distribute in space. The particle behavior is about how detection happens in localized chunks. But the underlying reality is neither, it's quantum amplitudes. Let me make this concrete double slit experiment. You shine light at two slits. What happens? Classical wave picture says light wave passes through both slits, splits into two waves. These waves interfere on the screen, creating the pattern. Classical particle picture says each photon goes through one slit or the other. You should see two bright lines behind the slits. Neither of these is right. Quantum mechanics says each photon has a probability amplitude for going through slit A and a probability amplitude for going through slit B. These amplitudes add, they interfere. The interference of amplitudes determines where the photon is likely to be detected on the screen. But the photon doesn't go through both slits like a wave spreading out. And it doesn't go through one slit or the other like a particle making a choice. It does something that can't be described in classical terms. The amplitudes interfere. That's the correct description. You detect the photon at one location on the screen. Click localized looks like a particle, but the probability of where it clicks is determined by interfering amplitudes. Looks like wave interference. It's neither. It's quantum. Here's the thing that really bothers me about the wave-particle duality language. It makes people think light switches between being a wave and being a particle, like it's one or the other at different times. But that's not what happens. Light is always the same thing, a quantum object. What changes is how we interact with it, how we measure it, how we describe what we measure. When you don't measure which slit the photon went through, the amplitudes for both paths interfere. You see an interference pattern. People say it behaved like a wave. When you do measure which slit, you collapse the amplitude. Now there's no interference. You see two bright patches. People say it behaved like a particle, but the light didn't change. Your measurement changed. Your interaction with the light changed. The light just did what quantum objects do, evolved according to quantum mechanics. Let me give you another example that shows how misleading the wave-particle language is. Take an electron. Electrons are supposed to be particles, right? They have mass, they have charge, they're localized. Definitely particles. But do the double slit experiment with electrons, one at a time. Build up the pattern, you get interference, just like with light. Does that make electrons waves? Are we going to say electrons are both wave and particle too? Yes, that's exactly what people say. All matter exhibits wave-particle duality de Broglie wavelength. Everything is both. This is taught as a fundamental principle, but it's the same confusion. Electrons aren't waves. Electrons aren't particles in the classical sense either. Electrons are quantum objects. Their probability amplitudes interfere. That's why you see interference patterns, not because they're waves, because they're quantum. You can do the same experiment with atoms, with molecules, with bigger and bigger things. As long as you maintain quantum coherence, as long as you don't destroy the interference through decoherence, you'll see interference patterns. Not because these things are waves, because they're quantum objects whose amplitudes interfere. The wave language comes from classical physics. In classical physics, there are two kinds of things, particles and waves. Particles are localized. They have definite positions. They follow trajectories. Waves are spread out. They have wavelength and frequency. They interfere and diffract. These are the only two options in classical physics. So when quantum mechanics came along and showed behavior that didn't fit either category, people tried to force it into those categories. It's both. It's sometimes one, sometimes the other. It has dual nature. But this is wrong. Quantum objects aren't classical particles or classical waves or some hybrid. They're a third category, a quantum category. They follow quantum mechanics. And quantum mechanics doesn't reduce to classical wave theory or classical particle theory. The math of quantum mechanics involves complex amplitudes. These amplitudes evolve according to the Schrödinger equation, or in quantum field theory, according to field equations. When you calculate probabilities, you square the amplitudes. When you have multiple paths or possibilities, you add the amplitudes before squaring. This addition is what produces interference. That's it. That's the whole story. There are no waves in the classical sense. There are no particles in the classical sense. There are probability amplitudes, and they behave according to specific mathematical rules. So why do we keep using this language? Why do textbooks still teach it? Because it's a useful approximation. In certain situations, the quantum object behaves approximately like a classical particle. In others, it looks like classical waves. The math is similar to wave equations. So as a pedagogical tool, we say sometimes wave-like, sometimes particle-like. It helps students connect to familiar concepts before diving into full quantum mechanics. But it's a crutch. And if you never let go of the crutch, if you keep thinking in terms of waves and particles, you'll never really understand quantum mechanics. You'll be stuck in this halfway house where things are mysteriously both and neither. And it all depends on observation and consciousness and philosophy. That's not physics, that's confusion. Here's how I teach it. I don't start with waves or particles. I start with probability amplitudes, complex numbers with magnitude and phase. They evolve in time. You add them when there are multiple possibilities. You square them to get probabilities. Then I show examples. Double slit interference. Not because light is a wave, but because amplitudes from two paths add, and when you square the sum, you get interference. The pattern emerges from amplitude addition, detection. Lalized clicks. Not because light is a particle, but because when you measure, the amplitude collapses to one outcome. The detection event is discrete. You build up the theory this way: amplitudes, evolution, measurement, no waves, no particles, just quantum mechanics. And when students understand this, they stop asking, is it wave or particle? They stop trying to visualize what an electron looks like. They stop thinking observation creates reality. They understand quantum mechanics is about calculating probabilities. You have amplitudes, you evolve them, you predict outcomes. The rest is interpretation. Philosophy not necessary for physics. Now you might ask, what is an amplitude? What is this complex number physically? I don't know. Nobody knows. And that's okay. The amplitude is a mathematical object that lets us calculate probabilities. We know how to manipulate it. We know the rules. We compare predictions to experiment. They match perfectly. But what it is in some deeper sense, I can't tell you. Maybe the amplitude is physical. Maybe it's epistemic. Maybe these categories don't apply. Physicists have argued about this for a century. Copenhagen, many worlds, pilot wave, cubism. Each has its defenders. Each has its problems. Experiment doesn't distinguish between them, so I don't worry about it. I calculate, I predict, I compare to experiment. It works, that's enough. But I'm careful about language. I don't say light is both wave and particle, that's misleading. It suggests light switches between two classical forms. I say light is a quantum object. It behaves according to quantum mechanics. Sometimes it resembles waves, sometimes particles, but it's neither. It's quantum. This is more precise, more accurate, less confusing. And the confusion matters, because when you think light is both wave and particle, you start asking wrong questions. You start thinking observation determines reality. You start bringing in consciousness and mysticism. I've seen this happen. People take wave-particle duality and say quantum mechanics proves reality is subjective, or consciousness creates reality, or you can manifest things by observing them. Nonsense. That's not what quantum mechanics says. Quantum mechanics says you calculate amplitudes and predict probabilities. The wave-particle language taken too literally leads people astray. So I'm careful. I use precise language. I emphasize the math, not because I'm a killjoy, but because I want people to understand actual physics, not a distorted, popularized version. Light is not a wave. Light is not a particle. Light is a quantum object described by probability amplitudes. Sometimes those rules produce wave-like patterns, sometimes particle-like detection events, but the underlying reality is quantum, not classical, not hybrid quantum. And if you understand that, really understand that, you're on your way to understanding quantum mechanics. Not perfectly, nobody does, but accurately, without the confusion from forcing quantum into classical categories. That's what I try to teach. That's what I wish everyone understood. Quantum mechanics is strange, yes, but it's not mystical. It's not paradoxical. It's just different from classical physics. Learn the rules, calculate with amplitudes, predict outcomes, compare to experiment. That's physics. Not by calling it wave or particle or both, but by treating it as what it is, a quantum object following quantum rules.